Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, Basic Circuit Concepts. Under Basic Circuit Concepts, Sheet Resistance. In our previous topic, we have completed the layout design rules based on CMOS design and taking the rules into consideration, we have done few examples few examples for the circuit schematics. We have drawn the layout diagrams based on CMOS design. Now we are going to discuss sheet resistance as a part of basic circuit concepts. After the completion of this lecture, you will be able to examine the concept of sheet resistance, which helps in evaluating the effects of interconnections or wiring in the circuits. So the wiring up of circuits takes place through various conductive layers in MOS processing. So in MOS processing, as we have learned in MOS fabrication, it starts on a silicon substrate with the design MOS with P substrate, then with silicon dioxide layers, and then so many photolithography processing, and all the layers are stacked up. So each one is through various conductive layers. So in order to evaluate the resistive and capacitive characteristics of those layers, we need to be aware of this concept. Concepts such as sheet resistance and standard unit of capacitance help greatly in evaluating the effects of wiring and input and output capacitance in such scenarios. It is not a normal conductive wire or a conductor. Instead, those are layers on one above the other in order to fabricate a device. In order to evaluate the resistance and capacitances of these, we require the concepts of sheet resistance and standard unit of capacitance. So in this topic, we deal with sheet capacitance. So sheet resistance. So sheet resistance. Just we will consider like a layer in our MOS fabrication. So we consider a slab, uniform slab like this, which is of conducting material with a resistivity of rho and width W. So this is the width, and thickness is T, and this is the thickness, and length between the faces is L. So this one from here to here, this is L. So with reference to the figure considered, we can write our basic equation of resistance as R is equal to rho L by A, whereas that is between the faces A and B that were marked. So we are writing RAB as rho L by A, units are ohms. So where in this rho L by A, where A represents the cross-sectional area means this cross-sectional area. So what is this cross-sectional area? This width multiplied by this thickness. So T into W. Now if you consider this slab to be a square, then what happens is length and width will be equal. L is equal to W. So in that case, this equation changes to RAB is equal to rho by T. So such resistance is known as sheet resistance, ohm per square or sheet resistance. So RS, sheet resistance, is rho by T ohm per square, where we can observe from this equation RS is independent of the area of the square. That means what? If that is a square shaped slab, if you are having a 1 micrometer side square or 1 centimeter per side square, the sheet resistance will remain same provided the thickness is same. Hope that is clear. So now we have few points based on this equation that has been derived. Sheet resistance of layers depend on thickness of the layer and resistivity of the material. This is the resistivity and this is the thickness. Where evaluating this resistivity and thickness for metal and polysilicon layers, that is easy. So in our MOS fabrication, the major layers are metal layer, polysilicon layer, substrate, and diffusion. So the both the metal, poly or substrate, evaluating the thickness or resistivity is very easy. But whereas for diffusion layers, here it is marked for diffusion layer, the depth of the diffusion region results in effective thickness. In order to get Rs is equal to rho by T, so thickness is given by the effective depth of diffusion into the MOSFET, while rho is determined by the impurity or doping level or profile that is going to determine the resistivity. So here few typical values of sheet resistance are tabulated for different technologies of 5 micrometer, 2 micrometer and 1.2 micrometer for various layers, metal layer, diffusion layers, N transistor channel, P transistor channel, polysilicon and silicide also. So this can be used as a reference, that's all. Then let us apply the concept of the sheet resistance to transistors and inverters. So let us start with a transistor. So here see, this layout represents a transistor where this hashing we are using it for diffusion. Let us consider the opposite hashing is for polysilicon. So this forms the source and this forms the drain. So obviously this would be the length of the channel and this would be the width of the channel. Both are 2 lambda and 2 lambda respectively. So what is the resistance of this transistor is, so this overlap is forming a square. Square means R is only 1:1 ratio only. So 1 square multiplied by the sheet resistance. So what is the typical value of sheet resistance in 5 micrometer technology is 10 power 4 according to our previous table here that has been marked. This one has been taken into consideration. So here length to width ratio is denoted as Z, that is 1:1 in this case. We consider one more case here. This is also a transistor where see length of the channel is marked here means this should be the source and this should be the drain, and this one is our what we say diffusion, and this is our polysilicon where length is marked as 8 lambda and whereas width is 2 lambda. So here the Z, that is length to width ratio, is 4. So in this case the channel resistance, that is the transistor resistance, is Z times multiplied by the sheet resistance, that is 4 into 10 power 4 ohms, or otherwise alternatively you can say, so that channel can be regarded as 4 squares in series. So this one you can say it as 4 squares in series. This is 1 square, second square, third square and fourth square. So definitely in the previous case for 1 square, that is 10 power 4 ohms, means 4 squares means 4 into 10 power 4. Hope that is clear. So when you make it a inverter resistance calculation, see here, this is an NMOS inverter and this is a CMOS inverter. So an NMOS inverter, the pull up LPU to WPU ratio is marked as 4:1 and pull down LPD to WPD is marked as 1:1. So here this can be 8 lambda is to 2 lambda example, just know what we have seen. So where we can regard the ZPU as 4. So in this case the sheet resistance will be 4 into 10 power 4. 10 power 4 is a typical value. So that represents what? 40 kilo ohm. And here 1:1 means we can regard it as 2 lambda by 2 lambda. So in this case this is only 10 power 4 the resistance, so that is regarded as 10 kilo ohm. So what is the on resistance of this inverter is this is a series combination. So this is 40 kilo ohm and this is 10 kilo ohm put together. On resistance, when this is on, this will be always on. So on resistance will be 50 kilo ohm. Whereas in CMOS inverter, as we have learned, the aspect ratio is always 1:1. So length to width ratio of pull up is 1:1. Length to width ratio of pull down is 1:1. So in this case ZPU is 1. So R on is treated as 1 into sheet resistance of PMOS, that is 25 kilo ohms according to our typical values table, and pull down is 10 power 4, that is 10 kilo ohm. But we can't say the on resistance of this circuit. Why? Because for a given input voltage only one transistor will be switched on, the other transistor will be switched off, and vice versa. So ratio rule does not apply as there is no static on resistance from supply to ground. Hope this is clear. So based on this topic, there are a few lecture level questions that have been framed. Please have a practice of these questions for a good understanding. That's all for this topic. Thank you. Happy learning.